The broadcast is now starting. All attendees are in listen-only mode.
Hey everyone, Cam from Odell here. Thanks for joining us for another installment of Isolation Intelligence. Today we have Dr. Marwa Zaatari. She's the Vice President of Building Solutions at enVerid, and she's going to be talking to us about the latest updates to ASHRAE 62.1, especially where it pertains to indoor air quality. The last 15 minutes of the presentation are going to be specific to COVID-19. And just before we get going here, a couple housekeeping things. If you have a question at any point during the webinar, you can ask questions over on the right-hand side. There's a question box. We'll try and get to all the questions at the end, so we're not interrupting too much. But if you do have something that's pertinent to what we're talking about right now, you can raise your hand and I'll cut in and we'll get that question answered right away. There's also a copy of the handout available under handouts. You can follow along with the presentation, and at the end there's some bonus slides that we won't be covering in this presentation, but just a little bit of extra information that you can take a look at. As with all of our webinars, the recording and the handouts will be available on our website afterwards. So if you don't get a chance to watch the whole thing, or if you want to revisit for some updates, you can check that out afterwards. So without further ado, I give you Marwa Zaatari. Go ahead, Marwa.
Thank you, Cam, and good morning, everyone. As Cam mentioned, I'm going to talk to you today about regulatory update, specifically from ASHRAE Standard 62.1. And for the last 15 minutes, we have bonus slides regarding COVID-19, also update from the ASHRAE Epidemic Task Force. This is the agenda for today. The challenge we face, we design buildings, what's new and proposed in ASHRAE Standard 62.1 2019 version. I'm going to talk specifically about the two procedures for mechanical ventilation rates. The first one, the ventilation rate procedure. The second one, the indoor air quality procedure. And as I mentioned, we'll finish by COVID-19 insights. So I will be focusing my talk today on the 90%. The fact is that most of us spend about 90% of our time indoors. You probably have heard many people say this. So that's around 22 hours per day. And the majority of our exposure to outside air pollution actually happens inside. And you can add to it indoor pollution from building, furniture, people, and people-generated activities. As a result, our indoor environment has so much impact on our health, so much so that according to Harvard Public School of Health, they say that the building manager, so your building manager has more impact on your health than your doctor. And as you can imagine, this is even more important in the age of COVID-19. So what do we do about this? The traditional approach is to maintain indoor air quality in buildings is to bring outside air. And the premise is that you bring outside air to dilute indoor pollutants. However, what happens is that when you bring outside air and it's too cold, you need to condition it. It means that you need to spend more cooling and heating energy, maybe more relative to our talk today. And then in turn, basically spending more energy will lead to higher outdoor emissions, and you will be contaminating your building even further with outdoor pollution. This is what I call the vicious cycle. And it means that buildings maybe should not depend on outside air as the solution for acceptable indoor air quality. And this is especially true if you live in a polluted dense city, or for example, your outdoor air intake is next to a pollution source. So the question that is basically on the mind of the ASHRAE Standard 62.1 committee, can we do better? Can we find strategies that maintain indoor air quality and at the same time lower energy consumption? So a project can meet both its indoor air quality goals and energy efficiency goals. So I'm going to give you some highlights about this big picture from ASHRAE Standard 62.1. So ASHRAE Standard 62.1, it's called Ventilation for Acceptable Indoor Air Quality. I have to say it's used to call that. In 2019, there is an addendum that was approved that changed the name of the standard, and later you will know why. So the new name of the standard is Ventilation and Acceptable Indoor Air Quality. So they took the 4 away and put instead the and. And this is basically, it's a subtle change, but it's the first indication that ventilation might not be the solution to all our problems in buildings. Now, You might be familiar that there are two procedures. And this is, we're talking about intentional mechanical ventilation for commercial, educational, institutional, governmental buildings. We're talking about the ventilation rate procedure. You will see me referring to it as the VRP, and it's a prescriptive approach. It's one size fits all. It's basically based on how many people you have in the building and the size of your building. There's a bit more math, but basically it doesn't matter where you live or what's inside your building. This is one number that fits all. And you can imagine from the intent of this procedure why there's problems. The second procedure, which I'm a big fan of, it's called the Indoor Air Quality Procedure, IAQP. It has been in a standard since 1979. It's a performance-based approach, and if designed properly, it will lead to energy conservation and at least less outdoor air pollution. One more benefit is maybe acceptable indoor air quality or enhanced indoor air quality, depending on your project goals. So starting first is what's new in 6.2.1 ventilation rate procedure. And if you are a designer, a mechanical engineer, you probably use this procedure every single day. So there are in total 13 new addendums in 6.2.1, 30. The standard has been basically in 2019 in a major changes. I'm going to share with you today 5 changes only regarding the ventilation rate procedure before shifting gears to the indoor air quality procedure. So the first one is called unusual sources. So the committee added in the 2019 version basically a requirement for source strength. And what they say is basically, if you don't know everything in your building, if you don't know the sources of pollution, indoor and outdoor, you cannot use the VRP anymore. And this is very powerful because this is the first time that the standard acknowledged that the ventilation rate procedure is actually risky, because it was meant as basically numbers, like let's say 17 CFM per person per office, to just be as a starting point, and we need to do better as the time goes. But we skipped a few decades for that. So to give you an example that I basically was aware of is the Amazon headquarters in Seattle has 7,000 dogs. 7,000 dogs. So if you are a mechanical engineer designing for this office buildings for 7,000 dogs, so people plus 7,000 dogs, what would you choose as a space type under the ventilation rate procedure? Would you choose an office building or an animal facility? The answer is that you cannot use the VRP for this type of application and many different applications, because there is more a chance that you will not know what you're designing for, and you need to do the indoor air quality procedure. The second one is the ventilation efficiency. And I'm personally very excited about this. Basically, you used to do the math and say you need 5 CFM per person, 0.06 CFM per square foot for office, and then you need to do like 2 pages to figure out the ventilation efficiency. So for you to calculate the total volume of outside air that you need to your building, and we're talking here about a multi-zone building. Or you need to go to appendix, so you use this table, ventilation efficiency, and you see this number is 1 or less, so you need to increase your outside air depending on your findings. Or you need to go to appendix A and do a little bit like more exhaustive calculations. The problem was few VAV systems will fall under this table and it will not be used, and this will force the use of a more complex appendix A. So what they did, they took, I don't know exactly the number of projects, but 100 of them, and they analytically came to these 2 equations. So imagine like 2 pages and a much more complex appendix is all condensed in 2 lines. And these 2 lines depend on the diversity that you're taking for your building. So simply, if you have the diversity more than 0.6, you just divide by 0.75 and that's it. And that have a very good implication for people renovating their buildings, or as I show you a little bit later, if you're applying to have a LEED project, or you know, it will be much easier to check, to do the calculation and later to check. And you can build this in your Excel calculation, the MZ1 in ASHRAE, instead of using the exhaustive calculations. Moving on for demand control ventilation. So demand control ventilation, you need to design per the VRP, and then you need to install sensors to indicate the occupancy of your space. Typically, most people install carbon dioxide sensors. And the correct way to do it, I cannot stress this enough, is that you are not allowed to set a limit, and above this limit, you increase ventilation. This is not correct. You put CO2 sensors in each and every ventilation zone, and if you sense that new people are coming, you need to increase your ventilation rate. This is really important. This is the correct way and the intent of the standard. So up to 2016, there was no requirements for accuracy of the CO2 sensors used for this procedure. Various research projects, very well documented, they show a wide variation in accuracy and the drift of the CO2 sensor. So simply, 2019 now added language from the 2013 California Title 24 about the requirement of the CO2 sensors. And I put them here. There is a requirement about accuracy. Sensors need to be calibrated. They need to be certified. They don't need calibration no more frequently than 5 years. And finally, you need to put sensor failure controls. So if they fail, you need to go back to the full design, which is the VRP. I have two more. One regarding adding an appendix and added this table. The advantage of this table is a simplified ventilation rate for existing buildings. And this appendix is intended to be used to assess ventilation rates in existing buildings when you do third-party evaluation programs, such as ASHRAE Building EQ, BQ, LEED EBOM, Energy Star, etc. And this appendix will provide you with the zone minimum primary airflow and is included as a guidance. You can evaluate and adjust your minimum box settings. Note that this informative appendix is not intended to be used as regulatory or permitting. It's just basically to check. You know, you can check if you're renovating your building, or someone is asking for, you know, if we're doing it correctly or you're doing audit, you can simply check these numbers. Last one, and it might be, you know, relevant more relevant now in this age of COVID-19, is the 2019 added ventilation requirement and ventilation numbers for outpatient facilities and animal facilities. And the story here is the 2018 of the Facility Guideline Institute. If you're not familiar with that, this is basically the guideline that say about the design and construction of outpatient facility. They basically say for outpatient facilities, you need to meet local ventilation code. So you go to the IMC or UMC. So the IMC and UMC, they reference ASHRAE Standard 62.1. ASHRAE Standard 62.1 reference ASHRAE 170, which is the healthcare. And ASHRAE 170 reference ASHRAE Standard 62.1. So it was, you know, cyclic reference, and no one has the spaces, and it was always a point of contention. What should we do about these spaces? So now finally they found home, which is ASHRAE Standard 62.1. You can go today and open it, and if you're designing any of these spaces, you don't need to be conservative as much as basically surgery or patient facilities. You can use 62.1, and also you can use the indoor air quality procedure for these spaces. Moving on. So our next topic here is the indoor air quality procedure. So the indoor air quality procedure, as I mentioned, has been in the standard for a really long time and is a procedure with significant flexibility. And it will allow you to put your indoor air quality goals, your energy goals on the table, on the design from the beginning, and achieve a differentiator. If you are a designer, you can achieve a differentiator in your design. Or if you are a building operator, you can have a much better solution. So what is it about? Or basically the proposed change, before I go about the procedure, the proposed change was specifically intended to minimize the risk on the engineer behalf by specifying the requirement, to make it more stringent, and by more stringent, make more specific, to say, where do you get the efficiency of the air cleaning solution? What about byproducts? And to make requirement much more prescriptive, because You need this. You don't need, as an engineer or designer or rep or building owner, you don't need to worry about go figure out the research. You can come to the standard and you have it, the procedures laid down. And at the end of the day, you use a calculator basically to go through the different calculations. But I would like you to know the details behind this procedure. And later you'll be provided basically with a calculator to go through these calculations, similar to the ventilation rate procedure, basically. So what is it about? So basically, you basically have contaminants of concern in your building. For example, carbon dioxide, some volatile organic compounds. You have to maintain them below certain limit. You have to identify an air cleaning solution if you're using one, and then using a mass balance equation. So they were not defined, and a big basically push from the committee is to define those requirements and make them as prescriptive as possible. Now, it doesn't apply to ASHRAE, and I'm not going to go through it in details, but if you have a LEED project, you can apply the same procedure to the indoor air quality procedure pilot credit in LEED. And for that, you need to do only one time, an indoor air quality test. There's also a survey, but I'm not going to talk about it today for time purpose. So in ASHRAE, there is always two schools of thoughts. There's one school that say ASHRAE is a health standard. Another one say that ASHRAE standard 6.2.1 is a comfort standard. So the choice of the terminology and what we're trying to do is very important. So the first thing that basically was changed in the proposed addendum is what we call them. We used to call them contaminant of concerns, or COC. Change this terminology to say design compounds. And this is actually important because the goal is not to put an exhaustive pollutant list and burden the engineer. The goal basically is to find a very short list. And if you control for the short list, it will result in an acceptable indoor air quality. And by the way, this is the same concept, same underlying concept of the ventilation rate procedure. These numbers, 17 CFM per person, had the same intent, acceptable indoor air quality, based on the idea of you have pollutants and you have to manage them. So this is not a foreign concept, just a more refined concept. And then, so we have compounds, and people made the argument that PM, particulate matter, less than 2.5 micrometer is not a compound. This now we have design compounds and PM 2.5. And basically, this is the proposed list. As I mentioned, a very short list and representative list. And notice is ammonia only if you have animal in your space. How did the committee came up with this? There's 4 simple questions. First one, is this compound expected to be found in the indoor air with a reasonable frequency at concentration relevant to the design target? And by design target, I mean concentration limit. Number 2, is there a design target that has been proposed by a cognizant authority? So as you know, ASHRAE does not make up health limits or concentration limits. ASHRAE merely reference other cognizant authority. Number 3, does it seem reasonable to expect we find product emission rate for the building or product specific? Number 4, if you want to measure it, can you measure it? Is there a method for it? Moving on to concentration limits. So this is the list, and this is basically instead of concentration limits, they call them design target. Part of this procedure is that this is the minimum list. You can use more if you want. And these design target came from a cognizant authority. And I have to note something that the committee discussed over and over. Using occupational exposure limit is not acceptable. This is really important because some of these limits that are not here, basically, OSHA limits, are not developed for your typical office buildings, and we see it often. So limits meant from OSHA are meant for industrial applications. They're not meant for basically students or office workers. So if you see that, you can see the design target and the cognizant authority. And you'll have these slides, you can go through them basically. Identifying an air cleaning solution and efficiency. This is very important. In the equation, if you're using an air cleaning solution, you need to define it. Yeah, you need to use this number, and this number has to come from somewhere. It cannot be made up. So, unfortunately, you have many ASHRAE standards, and you have ISO standards, and maybe others. It has to be third-party test. So, when you are an engineer and looking at this, you need to ask, this efficiency number that we're using, or from a manufacturer, where did it come from? And I list here for your knowledge about the standards we have in ASHRAE today. Most of you are familiar with ASHRAE Standard 52.2, and it applies to particulate filtration. We call them filters. And it's a duct test. You put the filters, you measure before and after, and you measure for a different particle size, and you get a MERV, minimum efficiency reporting value. I don't know if you know about this. It's called Standard 145.2. I like to think about it as the equivalent of 52.2, but meant for gas, meant for molecular air cleaning. And this is for, you can use it for VOCs, aldehydes, ozone, basic and acidic gases. And it's very similar to the 52.2 test. Same idea. You have a duct, you put your material inside, you measure before and after. You know the efficiency, certain time requirements. Give you an example. This is the efficiency to measure ozone. And it's taken from a third-party research Triangle Institute. Basically, you challenge your product with a known ozone input concentration. In this case, it was 70 parts per billion. And then you measure before and after for a certain amount of time. You calculate the efficiency. This is how you should see it. Furthermore, you can do a byproduct test. Byproduct test is known to be for ozone, but it's not only for ozone. Some air cleaners are known to produce other oxidants, known to produce formaldehyde, ultrafine particle matter. So look for this for specific. Last in this row is to use the mass balance equation. So you look here, and this is actually the equation. It looks complicated, but actually it's not. I will walk you through it. So as you know, and as I mentioned before, in our indoor environment, there are pollutants related to us, generated from us. Example is carbon dioxide, the most basically abundant and known. And there are pollutants, mainly the source are from furniture or building, etc. So N is the emission rate. So let's say you're talking about carbon dioxide, and we know the emission rate for example, adult, male or female at rest. And we know the number. You can simply calculate N, the emission rate. And your goal is to keep this CBZ, concentration at the breathing level, below a certain limit. And this certain limit you can take from the addendum, or you can even define more ambitious limits. So traditionally, when you do the ventilation rate procedure, you only use this part, and you see minus because dilution supposedly will help if your outside air is not polluted and you're not bringing more harmful pollution to the inside. So the dilution is depending on the volume of outside air. The more the volume, the better, and the concentration. Now we add to this air cleaning. And if you're using air cleaning, it means you are substituting part of the dilution with air cleaning. And perhaps this way you can have a flexible method, and you can basically see the trade-off between more air cleaning and less dilution, and make basically iterative process to arrive to your optimized project goals. We'll end with this about the indoor air quality procedure. So through designing for the indoor air quality procedure, there are some cases that makes a lot of sense to use the indoor air quality procedure. The first one, if you live in a city where it's polluted, the most straightforward to say that if you are a non-attainment, or if you have pollution in your dense city, if you have your building outdoor intake next to a bus stop, or next to another building, or a local source of pollution, or next to a highway. Second one, if you have a building today that you are renovating or doing densification, but your HVAC system capacity of outside air, you cannot you cannot basically meet the outside air requirement, it makes sense to say, this is how much I have today, and I want to add people, or my HVAC system is aging and I'm losing capacity, I'm losing comfort, how much air cleaning do I need? You can do that using the indoor air quality procedure. If you are designing a new building and for some reason you have limited HVAC capacity, like something that I dealt with, a geothermal project, they want the building to be fully geothermal and it's an event center, they couldn't, basically if they have a large event, they couldn't do the cooling of the outside air for the large event only using geothermal projects. So they said, this is how much we can afford, how much we can have, how much we need air cleaning to substitute the other requirements. Similar if you have a historic building you're renovating and you don't want to touch the DOAS or the central system. If you have a project goal with better indoor air quality, if you identify certain contaminant in your building, if you want to save energy, this is just, icing on the cake. And if you have a LEED building and you're interested to follow the indoor air quality pilot credit, this is an exciting opportunity because it might give you a lot of points to follow the indoor air quality procedure and actually directly controlling the indoor air quality rather than indirectly doing low emitting material and other tests. So in summary, I wanted to show you from the ventilation rate procedure and the indoor air quality procedure an example of different calculations. So let's say there's one person named James, and James sits by himself in a 200 square office. How much ventilation will be required for the different methods? And I know the Appendix F and Appendix A will not mean anything to you, but bear with me, there is a purpose for this slide. Appendix F is basically, if you want to do the least work possible, you go to an Appendix F and you get a number that applies basically CFM per square foot, 0.15. Similar Appendix L. Now you typically do this ventilation rate procedure. You say, I need 5 CFM per person, 0.06 CFM per square foot, then you need 17 CFM. And you need to assume some ventilation efficiency or ventilation effectiveness, depending if you're multi-zone or one zone. Just for the simplicity, we assume it's 1, just 70 CFM. Let us talk about personal ventilation. So if you're sitting next to your office, you have personal ventilation to you. It's not famous or widely used, but it's an option. End up with 15 CFM. Now, if you want to do demand control ventilation, in the case of James, because it's one person, it doesn't make a lot of sense because it's either occupied or not occupied by James. But if you want to do it, you need to respect that you still need 0.06 CFM times 200 because you cannot go below the area portion, which is 12 CFM. And there is natural ventilation if you need to pursue this. And finally, the indoor air quality procedure. For this example, you can decrease only to 5 CFM per person, granted that you did a good design. And this is how the graph looks. So on the y-axis, there is outside air CFM requirement. On the x-axis are the different procedures in the same standard. Some are in the body of the standard, some are in appendixes. And what I want to say about this is that I think about this graph this way. The more work you do, or the more investigation and performance-based oriented you are, the better your design will be and the more flexible. You arrive to hear the indoor air quality procedure. And the less work you do, if you just want to take a rule of thumb, is the more requirement that you need, and you'll be hit probably with a large capex and later OPEX size, and you're not going to be able to be competitive if you choose Appendix F. And similar as you go down. Okay, so I'm moving on a little bit away from the ASHRAE Standard 6.2.1 updates and proposed updates to the COVID-19 talk. And I'm sure we're all affected by this, and you'll be hearing about it a lot. So the first thing I would like to tell you is COVID-19 is a disease. So when we say COVID-19, we're talking about the disease. The name of the virus is SARS-CoV-2 or CoV-2, basically. It's a novel virus. We have no knowledge or experience or immunity to this pathogen, and it first made its appearance in 2019. And this SARS-CoV-2 is part of the coronavirus family. And if you're still wondering why the name of coronavirus, if you look at this image, if you see under a microscope, it simply has crowns. And the actual size of the virus is 120 nanometer. So if you look at this picture here, PM10 is 10 microns. And this is PM2.5 here. And this is the family of the coronavirus. To give this into perspective, the size, the diameter of the human hair is 50 micron. So you can imagine how small this virus is. Now, you heard a lot of talk in the news about, is it airborne or not, and what should we do about it? What is worth saying is that this virus, it has an envelope, positive sense, single-stranded RNA virus. It doesn't exist by itself. It needs to be attached to a fluid, a fluid. So usually it's attached to droplets or aerosols, so it cannot exist alone. So the actual size resulting of the virus is much more than 120 nanometer, depending if you are coughing, talking, breathing, etc. So two important questions that everyone is scrambling to answer from the ASHRAE and other organizations that related to the HVAC system. The first one is, what are the engineering interventions that can we apply in buildings when we go back to work and when we design buildings to minimize the spread of this disease? And how effective are those engineering interventions to minimize the spread? So saying that we need to do a lot of everything is just will not get us anywhere. We need to identify what things can help, what things do not help, and then we need to say, how can we prioritize these intervention measures and still meet our goals? First, about the airborne transmission. So the World Health Organization and the Center of Disease Control still maintain the same position, is airborne transmission is likely not driving the pandemic. And one of those associations is more aggressive than the other one. But in general, they say that we need to take care we need to do social distancing. We need to wear masks to be to minimize the spread of this aerosol via close contact. So they believe that close contact and then surface contact are driving the pandemic, and it's not the airborne route. There are many different studies, some peer-reviewed, some not, and some history lessons from SARS-CoV-1, so the SARS, and MERS, and measles before that tell us that these viruses can be an aerosol. In the next slide, I'm not going to go through it. I summarized some of the research that came in February. I didn't summarize the March one. There's a lot of research about this that basically they tested and they found it in air samples. So an indication is that it can be carried around in the building. It can be found on ventilation fans. It can be found in actual particulate filters. There's many studies and many talks about this. In the grand scheme of things, since we don't know for sure the route of transmission, and we don't know evidence-based which one is driving the pandemic, we have to take seriously that the COVID-19 can be transported via air, and we have also take seriously that the HVAC system can play a positive role in diminishing the spread of this virus. These are the studies, the 4 studies I talked about. There is much more historical studies about particulate filtration. I'm not going to go through them. You have them. Let me know if you need the links. So moving on to the question, what can we do about this? And you probably heard about many different ideas, and I'm going to go through them and show you, which I think it's very interesting, is a model that can prioritize the different strategies. The first one is filtration. So can filtration help? And we're talking here about specific is particulate filtration that's taking care of filtering the indoor air, so the indoor recirculating air. And the answer is yes. And this is published in ASHRAE. It's published in NAFA, the National Association of Filtration, and published by Professor Jeffrey Siegel from University of Toronto. He was actually my advisor. And I worked with him on this piece, just editing. He was the lead on this piece, and I was one of the editors. And basically, If HVAC filters are designed properly and are placed properly, installed properly, and there's no bypass, theoretically, they can help to remove airborne particles from air. And we have a sense that typically, the higher the MERV or the higher the efficiency, the higher the filtration. And HEPA filters, as you know, can mostly remove all airborne viruses. They have a very, very large 99.9% efficiency. And this applies as well to this to COVID-19 or SARS-CoV-2. Second one is UV. So ASHRAE, if you go to the ASHRAE website about the guidance, ASHRAE is a big supporter of UV. They specifically talked about UVC or UVGI, and the differentiator of those is the wavelength. We're talking about specific wavelength. UV is a proven technology, has been peer-reviewed to disinfect the air. It's similar to filters, similar to everything actually, need to be properly designed, installed, and maintained, right? And there are many different applications. Second or third question about electronic air cleaners. You can look at ASHRAE position document on filtration and air cleaning. You can look at the Jeffrey Segal publication, NAFA publication, and ASHRAE website. It all says the same thing. To date, there is no proof that these devices will reduce infection. Also, we, as ASHRAE committee, never obtained a third-party certification of efficiency. And there's concern about byproducts. As I mentioned before, it's not only ozone, it goes like beyond that, formaldehyde, ultrafine particles, etc. So you need to be very, very cautious in considering these devices and get the third-party proof, basically, of efficiency, efficacy. Last one is outside air ventilation. You know, for the first sense, it always makes sense that if the virus is indoor, then it makes sense to bring outside air to dilute it. And as a grand scheme of things, that's true, but there's two caveats to that, and I'm going to run through them. First one is relative humidity. Second one is outside air pollution. And then I'm going to put it in the context, which is more important to do. And can you do a strategy without increasing your energy consumption? And actually to be feasible. It's not feasible today to go oversize all your systems, especially the existing buildings, and will be even more important for the design of new buildings. So, adopting the Wells-Riley model, very highly adopted, is the first model to talk about measles in New York schools and later used by many different researchers. On the y-axis is the risk of infection. On the x-axis is the air exchange rate. And the different series here are MERV filters. Summary of this. Look at basically the yellow line. If you use a HEPA filters, it doesn't really matter what is your air exchange rate. Also, if you use a MERV 11 and onwards, in general, air exchange rate have minimal impact. And as you know, as I mentioned before, you know, HEPA is really good, but you don't have to go to HEPA and restrict airflow. MERV 13 will do, and MERV 11 will be better than the MERV 8 that you use today. To give you here an example, what I'm talking exactly about, this is an example, an office building, 40,000 square feet, 200 occupants. Air exchange rate of 6, which basically is, you know, meter cube per hour divided by meter cube divided by volume of building, will be 100% of outside air is your total supply. So we're talking about 40,000 CFM, give or take. The VRP is 4,500 CFM. IAQP in this case, 2,500. So 100% is 40,000 CFM. VRP 4,500. IAQP 2,500. You can see if you use MERV 11, really there's no difference between. You can see it's, you know, horizontal line between VRP and IAQP. And I would argue is that first, it's not feasible for you today in the summer or in the winter when you do it. It will not make sense for you to open your outside air if you're not in economizer mode, because you're not going to be able to maintain your comfort condition. So the premise from this to say is that, you know, if you use MERV 11 or more, if you can use higher particulate filtration, you'd be in very good shape in case the virus is airborne and going to your filters, you're going to probably be able to remove it. And of course, different MERV 11 has different efficiency. So as I told you before, there's two things about outside air that are very important. We know, and this was published a long time ago in ASHRAE handbook, is that relative humidity have a big impact on the survival of the virus. And basically they found is that if you maintain your indoor relative humidity between 40% and like 60 or 65%, this is the range, you're going to have the best chance to deactivate the virus. If you have low humidity or high humidity, the virus will live longer. And today I live in Boston. Still, it's really cold. I still can't open the windows really. And if I heat the indoor air to 22 Celsius, I'm going to have a relative humidity of 20%. So this is the problem, is that we don't use humidification in our building. So I want, as much as I want, to recirculate the indoor air through a really high MERV filtration. Not to say is that if I have a person infected in my house, I need to do social isolation. This is, the #1 defense. All what we're talking about here is supplement to the social distancing and the isolation. Two more points quickly about pollution. So I'm going to share with you two studies, and I put the links here because I think they are really, really interesting. So in Italy, they basically found that there is a high spread of contagion. And you've all heard in the news, basically we have China and Italy, but specifically the spread was in northern Italy. And this northern Italy, this region is referred to it as the industrial triangle. And this was after the economic boom, basically in the of the 60s of the 20th century, and is characterized specifically by high density of factories, traffic, and intensive agriculture. And what happened is that these researchers say, if you look at this graph, there is a positive correlation between number of infected people and the number of times they exceeded the pollution. In other sense, that particulate matter, and we're talking here about particulate matter 10 microns or less, they can serve as carriers or boost for this virus. The virus will not be deactivated, but attached to these particles and will be transported with them. And this is really sort of a little bit, a little bit frightening, but it's very important to take it into consideration. And first, I understand that this correlation doesn't mean causation, but we observe the same trend in China. There's another article about this. And recently in Bergamo, which is one of the hot spots in Italy, researchers took outdoor air samples. And these outdoor air samples, they found COVID-19 or SARS-CoV-2. So they are further saying that this is what they found here. It's not only a correlation, it's actually also a causation. To move on, a little bit related to particulate matter, but different flavor. So we know for a long time that particulate matter, specifically 2.5 or less, can penetrate to your lungs. It's a pollutant, and exposure to it will put more stress on your respiratory system in general. So a publication from Harvard Public School of Health, they said an increase of only 1 microgram per meter cube. And this is really important because we're not talking about only in China and India and Italy that we have severe pollution. Only 1 microgram per meter cube of long-term exposure to PM 2.5. And bear in mind, you can have exposure outdoor or indoor through bringing ventilation inside, is associated with 15% increase in the COVID-19 mortality rate. And this team even accounted for factors like smoking and population density. Still, they found a strong correlation. And this graph, the study is very interesting. I invite you please to read it. But this graph is basically, the top is the map showing county level, 17-year long-term average of PM 2.5 concentrations, 2000-2016. And then here, the county level COVID-19 death per 1 million population in the US. So this is two things to tell you that pollution have an impact on COVID-19. One is that it can impact mortality rate in this Harvard Public School of Health. And studies from Italy and China that I talked a little bit about before, they can help the spread of the virus and move it from the outdoor air to the indoor air if you're using strategies like ventilation. I think I'm right on time, 45 minutes. Thank you so much for listening to me.
Thanks, Marwa. I want to thank everybody for coming to this one. We do have some questions here, if you're ready for them, Marwa.
Go for it.
So the first question, does the updated ASHRAE 62.1 guidelines provide contaminant guidelines for different building types? And how is this used with the indoor air quality procedure and the HLR unit?
Yeah, so it's ASHRAE Standard because it's written in an enforced mandatory language. 2019 doesn't have it yet, but you can look. It's basically, it's an addendum in the last stage of public review. And the good news here is that it's one list that applies to all the spaces that are in 62.1. So it will apply for commercial, educational, government, gym. And just a reminder is it's a minimum list. You can add more if you want. If you want to take a look at this addendum, I can point you out where it is.
Okay, and with regard to the humidity slide, how is the risk of infection calculated?
This is, so 1 second, let me go back to it.
Yep.
So regarding to relative humidity, they talk about the survival of the virus in air. To give you an example, if you have the virus attached to a particle, and let's say the particle is large, 10 micron, if you have low humidity, it's going to evaporate, and it's going to be able to attach to small, basically, particulate matter and stay airborne. And it's not going to lose its integrity because it's going to be able to evaporate to a small size rather than to do by gravity and go to surfaces and be deactivated with time. There's a lot of big science about this. Dr. Stephanie Taylor, she's also associated with ASHRAE, multiple organizations, and she has some amazing, fascinating talks about why it's important to keep relative humidity between 40 to 60%. You can follow her on ASHRAE website, or she has her own YouTube channel, basically.
Next question, is there any current research on the virus spreading via HVAC systems in hospitals and long-term care centers that you know of?
Yeah, I summarized here a few of them. Before I start with this, there is basically, I think it's published in 2011. I need to double check this. But in Canada, specifically in Toronto, there was a study of 80 different residential buildings, and they found viruses, and this is a little bit surprising, up to size 30 micron on the actual particulate filters. They stayed there for quite some time. So we have from basically knowledge and on our basically particulate filtration world that yes, aerosols, particles, and sometimes large particles can be spread and can go to the particulate filtration, and we find them there. Now there are multiple studies. You can see here the Nebraska study. The Nebraska study, actually all the studies here, let me say 1, 2, 3, they were conducted in healthcare settings and in patient rooms where they were supposedly have COVID-19 positive and shedding the virus. In this Nebraska study, they actually took virus like sample in the air, and they found it in most samples. They also found it in the hallway, and they went to say that, you know, the doctors going in and out and the nurses, they transmitted into the hallway. In the China, in the Singapore study, for example, they didn't find it in the air, but guess what? They had 12 air exchange rates. And if you're not familiar with healthcare, they tell you you have to have an air exchange rate between 6 and 12. This one has 12. So they didn't find it in the air sample in the room, but they found it on ventilation fans. This can be explained as that, yes, it's presented in the air, and if you do circulation and you have high exchange rate, maybe you'll find it somewhere, and they find it on the fans. So there are much more than these studies. that basically are explaining that it can be airborne. And airborne is confusing because even if you cough and the particles will go by gravity and will settle, it's borne by the air, right? But there's more studies from Virginia Tech, Dr. Lindsay Marr, and a few other colleagues that talk about infectious diseases, and they tell you that they travel much more than 2 meters, and they can settle on surfaces, or they can be transported via the HVAC system, stuck on ventilation fans, filtration, depending on the characteristic of your system.
Okay, and just to remind everyone, these slides are available for download here in the GoTo program, and they'll also be available on the webinar or on our website at odelasoch.com afterwards. Next question here, does the contaminant testing by a third party have to be performed by a 145 certified agency?
1 second, let me go to that. So we're talking about this. So the problem we face today is that we know the standard for sorbents. So the standard for sorbents is mainly the 145.2, and sorbents are known and well documented, and you can read about that in the ASHRAE position document. Sorbents are known not to have any byproducts, and you can test them via 145.2 or via ISO. Now, there are some products, such as electronic air cleaners, they basically don't have any test. And they say they don't have the test because there's no method to apply to them. And I was personally involved in many different, ASHRAE meetings that ask these electronic air cleaners to give us what they did in terms of third-party tests. We have not received something. So in summary, you can have a different third-party test as long as, and I think this is the important part, as long as you can document what was the condition of your test. And more important, if you want to test efficiency, you need to make sure that you apply it in the field in the same way. To give you an example, what is the required CFM, or how much a piece of electronic device can clean? What is the area? What is the CFM? What is the voltage? And to do the efficiency test and the byproduct test for the same settings. And this can be done, I encourage, to be done in a third-party evaluation test. These addendums are still, we're still working on them. There's nothing official yet, but I encourage engineers to do their due diligence and ask for the manufacturer to do this using third-party tests and document efficiency, byproducts, same setting that they will design for in the IQP and their IQP.
Okay, thanks. And can we use ASHRAE 62.1 for ventilation in parking and road tunnels and subway stations?
So I'm aware there is basically an ASHRAE standard for transportation. If I look quickly, I have the ASHRAE standard 62.1 in front of me. I don't see specifically, I don't see parking lots, and I don't see anything related to transportation. I do see shipping and receiving, so I don't know if they're interested in this, but not anything. Oh, shipping and receiving, sorting, packing, light assembly, transportation waiting, like airports. Yes, but not enclosed parking garages, or some way where people wait. You can have it in ASHRAE standard 62.1. There is an occupancy category called miscellaneous spaces. Under it, there's transportation waiting, but that's the extent of the standard. You can look at the transportation one for more guidance.
Okay, and the asker of the original question about the contaminant guidelines has asked us to point them in the direction of the list. So if you could send that to me afterwards, Marwa, I can make sure that it gets to them, or we can go through it right now.
The list is on the slide, but the list is here, and I will be sharing the link later. I don't have it handy, and it's public.
Okay.
But the list is on the slides, and design targets also on the slides.
So we've got a few more questions here. Can the IAQ procedure be implemented simply to remove VOC contaminants, or does CO2 also have to be reduced?
So the indoor air quality procedure can be used only to remove volatile organic compounds, for sure. Yeah, can be used to use only volatile organic compound. I just want to caution, and this is, I heard this conversation in ASHRAE multiple times. You cannot design a space and say that 5,000 parts per million of CO2 is okay for our kids in schools, and say because OSHA said that. ASHRAE position on this, and you can further correspond with the ASHRAE chair of 62.1. These OSHA limits of 5,000 parts per million of CO2 are not meant for students, are not meant for office workers. These are industrial limits. And ASHRAE does not make a limit and does not reference to a limit. And also encourage you to look at the research from Harvard Public School of Health that links CO2 and productivity. Unfortunately, you cannot here include in this addendum CO2 because you will not gonna have a limit from a cognizant authority. And this is all health-based limits. So you can definitely only use it for VOCs. You need to calculate carbon dioxide and see what is the impact and maybe share with the engineer and the client. But I encourage you to add carbon dioxide to your list on top of this, and make sure to, to justify it, because you can't include it here in the text of the standard because you need the cognizant authority. But you can refer to Harvard. You can refer to many different peer reviewed that talked about students, productivity, students, and absence rates. And you can refer as well to the studies, basically that from Harvard that talked about that CO2 need to be no more than 1,000 or 1,100.
Okay, next one. Is it mandatory to have demand control ventilation for CO2 and other VOC contaminants?
So demand control ventilation does not talk anything about VOCs. It's not related to it. So carbon dioxide used as a proxy for human is the way that you can design per the VRP, so the full outside air needed, and then you can in operation decrease your outside air using the demand control ventilation, but that only take care of the pollutants supposedly generated by people. So you have a very small margin for offices of how much you can reduce your ventilation rate. So for office, you need 5 CFM per person, 0.06 CFM per square foot. So the portion that you can play with using demand control ventilation is only the 5 CFM per person. And you need to be able to adjust it dynamically. And this is something that, it's not applied correctly in a lot of different applications. You cannot set a limit. If you have 2 people, you put 10 plus 0.06 CFM per square foot divided by all the ventilation efficiency and effectiveness, etc. So demand control ventilation is primarily to help you to decrease outside air during operation, only when it pertains that if you have lower than designed occupancy, and if you know of that change.
Is it required? Do you have to use DCV?
No, demand control ventilation is totally optional in the standard 62.1.
Okay, next one. How do you do a basic condition assessment of building ventilation system filtration to determine if it will be effective to mitigate COVID-19 spread within the building?
Yeah, this is a great question. Basically, you can, there is on the ASHRAE website, ASHRAE, if you go to ashrae.org and you say learn more about the COVID-19, I'm actually on the ASHRAE Epidemic Task Force of Commercial Buildings. There is a lot of guidance, and the goal is that how do I shut down my building? How do I reopen my building? And what should I do specifically talking about now? There's more and more work about different space types and potentially in the future about designing of new buildings. And there are a lot of people are trying to publish stuff regarding the priority of filtration versus ventilation. The method that is published widely and accepted is called the Wells-Riley method. Now, I don't know if you remember the measles in New York schools. Measles New York schools, it was this guy, Riley, based on the Wells-Riley model that say, basically you have an equation, and this equation takes into account multiple things. One of them is that it's called quanta. Quanta means how many of this disease you have, it's 1 per hour, and how many of this disease you have, number per hour, that can infect you. There is the size of the virus that we're talking about, and then you can include different filtration and ventilation. I'm personally, helping the committee to run these models. We've done some work about energy recovery ventilation, if you're interested, and different work about residential, office, and schools. And for the person who asks you, I'll be happy to run different scenarios for the specific building. But basically, it's a model that's widely used, and I can give you the references of that and published, basically.
Okay, next one. Can you show the slide again with the effectiveness of the MERV 12 filters versus standard filters?
Is this the slide that we are on? But I didn't have MERV 12, I had MERV 11.
MERV 11, okay. We had a request to review the effectiveness of MERV 12 specifically.
Yeah, I don't have MERV 12. So MERV 12 does not exist. They go from MERV 11 to 13. This is the only slide I have it with a graph, but basically, just to tell you, this slide, it should be taken as the risk of infection as relative, right? It's based on a series of assumptions, but the best thing we know today is that to compare the relative infection or risk of infection of different strategies. There's a series of assumptions: how many people are infected in your buildings, the layout of your buildings, etc. And I don't know if the asked question, they talk about MERV 11 versus MERV 13, but MERV 11 is in orange and MERV 13 is in gray. And pay here particular care about the assumption and the particle size distribution of this virus. And this is not information from me. This information that has been widely published in the particulate filtration industry that talk about if we breathe or if we talk, if we sing, if we cough, what is the particle size distribution? How many particles are found between 0.3 micrometer to 1? How many between 1 to 3? How many 3 to 10? And then you take what we know about the MERV efficiency for each category, and you calculate an average size distribution. And then you incorporate in this model and you look. For me, honestly, this a little bit was surprising because, if we say, okay, let's all do MERV 13 and get done with it, or MERV 14 or HEPA, but come as a cost of, if today your system cannot move, or because, usually if you have high MERV, high pressure drop, it's not always the case, but usually is. If your fan cannot take HEPA filter, it's also very costly, or MERV 13, MERV 11 will be better than MERV 7, and MERV 13 and MERV 11 for this particular size that I assume based on previous research is very similar, and you can see here basically between the orange and the gray.
Okay, and then we just have two more here. Is there a specific disposal method for filters from an HVAC unit? I believe this is in context to COVID-19 and whether or not it can be effective when disposing.
Yeah, thank you so much for asking the question. Really, really important. And I should have said that. We have knowledge that the filters have microbiome and that virus can survive on these filters for a long time. And this is, hits home for you guys, because the study that I referred to it, the 80 residential buildings, they found the virus on the filters, and the virus survived for a long time after the filters was removed. So I'm going to repeat what Dr. Siegel said many, many different times. The reality is that we don't know for sure, but there is evidence that the virus will be on the filter from other research, and ASHRAE recommendation and NAFA recommendation is whoever is changing the filter to use personal protective equipment, gloves, and to put the filters in a sealed bag. This is really important for reps and service industries to educate and put signs and educate the industry about how to dispose of these filters. Really important.
Okay, and last one here. Can demand control be used in combination with the indoor air quality procedure?
So just to answer is that in principle, these are two different procedures, and it will not make sense to do both of them, because the indoor air quality procedure, if you use an air cleaning solution that can remove both the pollutant generated from human, pollutant generated from the area, you don't need any more the demand control ventilation. It will just add cost and more controls, etc. So in principle, you don't need the demand control ventilation. You can just go through the IAQP and design for your pollutants in the building. So this will be my recommendation. You can always combine multiple strategies and use it different times. You can always do that. I will give you an example. If you have basically a stadium and you want to use the indoor air quality procedure, and you have two settings of outdoor air and air cleaning, in case you have a match or you don't have a match, like you have basically like event or not an event, you can do that. But it can be all under the umbrella of the indoor air quality procedure. You don't need to go through the demand control ventilation.
Okay, well, that brings an end to our questions. Thanks, Marwa. On behalf of our team here at Odell, I want to thank you and your team at enVerid for giving this presentation. And I also want to thank all of our viewers for attending, and stay tuned for the rest of our upcoming isolation intelligence webinars. Just one last reminder, if you miss anything or you want to revisit any of the presentation, it will be available on our website to view again, likely by sometime tomorrow. You can also download a copy of the presentation yourself from our website. So thanks again, Marwa.
Thank you. Bye-bye.
Bye, everyone.